Hi everyone. I'll be talking about entropy of a freely expanding Fermi gas. It's fine, right? Okay, so I'll be talking about entropy of a freely expanding Fermi gas. This work is done. This is an ongoing work with Junaid, Abhishek, Anupam, and Manas at ICTS, Joel Lebowitz and Sheldon Goldstein at Rutgers, and David Hughes at Princeton. Okay, so let's say you have an isolated quantum system that you describe by some density matrix rho. And the commonly used definition for entropy in quantum mechanics is the von Neumann entropy. So the commonly used definition for entropy in quantum systems is the von Neumann entropy, which is just the negative trace of rho log rho. And if it's an isolated system, then the density matrix evolves unitarily, which is why, and we know very well that the von Neumann entropy does not evolve with time. But we also know that that doesn't work well with sit well with the second law of thermodynamics, which says that for an irreversible process in an isolated system, the entropy should increase. So what we would like to do is to define, instead of working with this definition, define like a Boltzmann entropy, which is like the usual log of the number of microstates kind of definition. For quantum systems that obeys this the second law. And I'll also show that we'll see that coarse graining happens to be the main ingredient to quantify reversibility rather than, for instance, interactions and ergodicity and so on. Then yeah. So the system that I will describe, so consider a circle, and you have, so consider a circle of length L, and in that circle, you consider a part of the circle of length, let's say A times L, where A is between 0 and 1. So that I'll just call box. And what you have initially is you have some fermions initially in thermal equilibrium in that region, in the box. And then at t equal to 0, let's say you just release the system, just remove the partition and let it freely expand. So it expands freely onto the full circle. So that is the system that I'll be talking about. Okay, so here I just describe, for instance, this basic quantum mechanics. So chi is the eigenstates and the ES is the eigenenergies for the box. And phi and the epsilon are the eigenfunctions and eigenenergies for the circle. So I just mentioned here in equation 1 and 2 because we'll be using them. Then as I said that the initial state is a thermal state on the box. So the initial multi-particle density matrix is described by equation 3, which is just a thermal density matrix written in the number occupation representation. That is the usual Fermi partition function. Okay, so from this multi-particle density matrix, we can compute the initial single particle density matrix, which is written here in equation 4. So here this F is just the Fermi function over the box energies, and these guys are the box eigenfunctions. And if we want to evolve it to compute it at a later time, so we have to first write it in terms of the circle eigenfunctions, because these box eigenfunctions are not a complete set of states on the circle. So we just do the transformation. I mean, this U is just the transformation from the box to circle eigenfunction. So you just write it in terms of the circle eigenfunctions. And once you do that, then you can straight away, very easily time evolve it. And the single particle density matrix at time t would be given by this equation 5. And from there, one can write down the expression for the real space density, the particle density in the real space on the circle, which is just given by this, the diagonal of the density matrix in the position space. So that is this expression 6. So, we can see that it has kind of multiple summations involved. And so it's not very helpful to deal with both analytically and even numerically for large system sizes, because the number of terms that you have to sum increases with the system size. So another way, so this one way of doing it. Another way of doing it would be to define. So what we do is we define this Wigner function on the circle. So for instance, it was for a circle it was defined in a paper by Mukunda in 1979, for example. But here notice that the slight change that we have is that it's defined for these Q values. Now, if you think, if you just assume the circle is of length 2 pi, then the circle momenta are basically integers, right? But the Q values that I have here, these are basically integers as well as half integer values. So we define it instead, this Wigner function is defined for twice as many points as you actually have for the circle momenta. And this is just the Wigner transform of the single particle density matrix. This is how it's defined. And the reason why we define it in terms of this Q instead of the actual circle momenta is because then it just satisfies this simple equation, which happens to be just the classical equation. So this is also the equation that is satisfied by the single particle density matrix, the single particle phase space density of a classical non-interacting system. So this also you can show that it satisfies the same equation, and which means that its evolution is very simple. You just have to boost the initial profile and you'll get the Wigner function at a later time. Okay, so we can solve this. We can compute the Wigner function for our system, which is this expanding Fermi gas. And I've just mentioned the expression here, which is given in this equation 9. Okay, so from here, how do you compute the real space density? That is just if you just integrate out the momenta, so you just get the real space density, and that is given. That is given by this equation 10, which actually happens to be the same as the earlier equation that earlier also I just it's the same equation. Okay, so so why do we introduce this Wigner function? Because so what we do as well is we define this classical Wigner function. And how do we define it? We define it as a product of the marginals of, we define it at the initial time as the product of the marginals of the quantum Wigner function, the actual Wigner function that I had in the, so this one in the red is the momentum marginal once you integrate out the position, and this one in the blue is the position marginal once you integrate out the momentum. So this one in the blue just says that it's the density is the real space density is uniform on the box. Basically, that's all it says, of length A times L. Okay, so this is how you define it initially, and then you let it evolve according to the classical equation. And that is very simple to do. You just have to boost this initial profile, so you just get this expression, which is in equation 12. This is a much simpler expression compared to the earlier one, and we can do some analytics with it as well. So for instance, we can try to compute the particle density from this classical Wigner function. And I've just written the expression, but it looks like the equation in 13. So one thing to note is that we can see that there's a separate steady state part, which is finally what it relaxes to as the uniform density on the circle, which is n over L. And then there is a time dependent part. So this we haven't tried to solve yet. But what we can do is if we just assume the initial temperature to be 0, initially that the system has a 0 temperature, then one can solve it, because then this Fermi function is just a box function to the Fermi momentum. And you can just, after you simplify it, so you get this expression. So this is a exact closed form expression for the particle density at 0 temperature. The evolution of the particle density at 0 temperature. And so this actually happens to match exactly with an earlier paper by Manas and others in a 2018 paper, where they studied various quench protocols for a Fermi gas at 0 temperature only. So that paper only talks about 0 temperature study. So this happens to match exactly. And well, this zeta, by the way, this is called what's called a Hurwitz zeta function. This is some generalization of the Riemann zeta function. But the only important thing to remember here is that whatever is within the square brackets, that is just some bounded oscillatory function of time. So the main, so we just have this 1 over T power law. Basically, that's how the density profile relaxes to the steady state value, and it will have some oscillations as well because of these terms. Okay, so now I will show, of course, this has been calculated from the classical Wigner function that we just defined by hand. So I'll just show some numerics. So this is for some low temperature. So as you see, the temperature is like mu over 50, where mu is the chemical potential. And this is some low temperature results. So what you see here is, on the, on this, in this curve, I just plotted the Wigner function at a particular value of x as a function of the momenta. And the blue one is the classical Wigner function, and the red one is the quantum Wigner function. And this is at initial time equal to 0, and the right this other curve is at some late time, and the density and the real space density has already kind of relaxed. So as we see that, of course, you can see very.
Saurav, you have 5 minutes.
They don't match very well, but then the Wigner function is not the observable, of course, the physical observable. Rather, we would like to see how the real space density, for example, compares. And that kind of compares very well. As you can see, so for instance, in this curve, the classical one, the density curve that you obtain from the classical Wigner function, and the red dots are from the actual true quantum Wigner function. They kind of match very well. So this is the density relaxation over time at some particular value of x. And here you see the relaxation of the density profile, the initial density profile over time. So it starts from this blue curve, which is like it has some uniform value in some part of the in some part of the circle, and finally it relaxes to the uniform value on the full circle. So similarly, this is for some high temperature results. So again, you see that the Wigner functions, of course, look very different, but the marginals again, I mean the real space density again matches very well at all times. Yeah. Okay, so now what I will do is I'll describe this coarse graining procedure. So what I call the U macro state, which is basically real space coarse graining. So what we can do is we can compute the number density, momentum density, and energy density from the Wigner function using these equations in equation 15. So once we do that, now what we do is that the coarse graining that we do is in real space. So you have the circle. So what you do is you divide the circle into some cells, some number of cells, and then you just compute the number of particles, the total momentum, and the total energy in each cell at a given instant of time, let's say, which is, of course, you just have to integrate these respective densities over that cell at that instant of time. Right. So now what is the U macro state? So the macro state is the U macro state at some time t is basically the collection, the knowledge of all these values, N, P, and E values for all cells at that time. So that is what defines the macro state, and it's coarse grained. I mean, it doesn't tell you the micro state exactly. So it's a coarse grained description. And so what we do with this description is, okay, so now let's just focus on one of the cells, let's say. So in each cell, what we do is basically we define some energy levels, and basically as the circle energy levels, but with the length of the circle identified with the length of that cell, which is here delta, let's say. And then we define some occupation numbers, occupation of these levels to be NKL. So NKL denotes the occupation of the kth energy level in the LH cell. Okay, and with this, of course, we have to satisfy some constraints. So the constraints are written here in equation 17 and 18. One more point is that we are doing it in the frame in which in the center of momentum frame of that cell at that time. So you just subtract the center of momentum energy, which is this term PL square over NL. So now you just have the number of particles and the effective energy, and you have to so you just have these equations, right? The total number of particles should be NL, and the total effective energy should be this much. Okay. So from here, this is basically like now you can basically do a counting, right? You can just count how many microstates, how many configurations which satisfy these constraints. And if you do that and then just take the log of the number of configurations, I call that the entropy of that cell. So you just get this expression, which is in equation 19. And the dominant contribution to this expression one can obtain by just assuming NKL to be of the Fermi form. So then then the entropy, of course, so this is how you define the entropy in each cell, and the total entropy is the sum of the entropies over all the cells. And this I just call as the Boltzmann entropy corresponding to the U macro state. Okay, so what we have to do here actually is that we assume this form basically, and we have to fit these equations and find some beta and mu, which satisfies these constraints. And once we get the beta and mu, then we can plug it here and compute the entropy for that cell. So in the next slide, I'll just show basically, so these simulations are very recent, and this for some low temperature case only. So here what I show is that, okay, so what we have done is divided the system into, let's say, 20 number of cells. And the empirical, so if you just look at this plot, so the empirical curve means that that's just the number of particles in those cells. So this whole these two plots are at some particular instant of time. So these just show the number of particles, the empirical values, and the fitted values is once you do the fitting with the Fermi form. So you get this. Okay, so as you can see that for this instant of time, the effective energy and the number of particles can be like fitted very well with this form. Okay, so here what I show is the number of particles again. So what I do is that I take let's say, as I said, we just divide it into 20 cells, the circle. So we just take the symmetrically located, like let's say the 5th cell and the 15th cell. So the 5th one would be the one which is initially occupied, right? Because initially from, let's say, from 1 to 10, in the half of the circle, we had the gas in equilibrium, and the 15th one is the one which was initially empty. So you can see they are symmetrically located, and again we do the same kind of, we look at this time, this is over time for these two particular cells, and you can see that except for the cell which was initially empty at the initial time, during the initial time, it matches well overall. But of course there are some deviations here, and that's because of the fact that initially you have like very few particles with very high energy in that cell, so it kind of happens to be like a bit tough to fit. And so this the last slide I will show is basically this entropy plot. This is entropy per particle over time, and as you can see that it kind of grows more or less monotonically and relaxes to some value. And so yeah, I mean, this is so far what we have done, and so this is one of the ways of one way of coarse graining the system, of course, but this is not the only way. And in fact, in yesterday there was Anupam's talk for a very similar problem, but for a classical system. And there he mentioned this one more coarse graining, which is what he called the F macro state, which is coarse graining in the single particle phase space. So that also is something we are working on for this system. Yeah, so thank you.
Thank you, Saurav. We have time for just one quick question.
Thanks. This depends very much on the initial state having been in thermal equilibrium, isn't it? Otherwise, being a free Fermi system, if you took it in some very, I mean, it's an integrable system. So if you took it in some special eigenstate, yeah, one of the, then it would not thermalize even if you expanded it. Is that correct? I was just wondering how sensitive are these results to your initial state that you have taken?
So actually, even in this case, when we take the system to be in thermal equilibrium in the box, even then the final state is actually doesn't really go to, I mean, thermal equilibrium. It's just that some of the observables obtain the equilibrium values, like the number density and a particle density and energy density. So I mean, for instance, if you look at so here, so this red one, this is the momentum's marginal. Which is like once you integrate integrate out the position from the of the quantum Wigner function. So this is not really I mean, it's some a times the Fermi function on the circle and over the circle energies with the initial temperature and chemical potential. So this is not really a Fermi function on the circle with some temperature and chemical potential. And so yeah, I mean.
But I thought you would fit it to something like that. I thought you, in a later this thing, didn't you try to fit it to some beta and mu or?
Yeah, so that this one.
Yeah.
So this only because, so up to this much, this expression is general. This just comes from the counting with subject to these constraints. But then this just gives you the dominant contribution to that log. I mean, this is log of some number of configurations, and that number of configurations, this just gives you the, like, it's like the saddle point approximation has this form for NKL. So we are not really, even though it looks like we are basically assuming some thermal equilibrium in these cells at this temperature, some local temperature and chemical potential. But yeah, I mean, we are not, because it's not like that the system. So for instance, these temperatures, finally, when this system relax, I mean, some of the observables relax. So these temperatures, these parameters, I'll just call them Lagrange multipliers. So this parameter, the beta S, will be the same for all of them. That won't really be, the system won't really be at thermal equilibrium at corresponding to that temperature. So this, like, just, yeah.
So can I make a comment? Hello? Yeah, so this locally we are using a ensemble transformation just for a calculation tool. So this in case we are not associating to any real densities. So it's just a number that actually helps us to compute the entropy locally.
Be saturated at some value, which I thought was the thermal entropy for the full circle, isn't it?
Yes, it's the thermal entropy, but it's only the sum, the value. But in the summand, this NKL, these are not any physical occupation to any levels of the full system. This is just on calculation. So for example, we want to compute omega, we do a Laplace transform to find out. So you have a Laplace parameter. So you can think of this beta and mu as the Laplace parameters in that sense, but they do not really mean any chemical potential or temperature local. It's not that.
Okay. Yeah.
Thank you, Saurav.